Hello friends, welcome to the lecture of integral equation and calculus of variation with the application and examples. We were considering the case of symmetric kernel. So if you remember, we were doing this problem, y of x equal to f of x plus lambda a to b k of x t y of t y of t d of t, provided that this k of x t is equal to k bar t of x. So here we are assuming that we have a symmetric kernel, and then we try to solve the Fredholm integral equation of second kind with this thing. So for that we have already discussed theory corresponding to eigenvalues and eigenfunction and how to solve this kind of equation. Let us apply that theory to solve our problems. So our first problem is this, y of x equal to x plus 1 whole square plus a to b, here a is minus 1 and b is 1, xt plus x square t square yt dt. Now if you look at here, f of x is your x plus 1 whole square and lambda is basically 1 here, and if you look at kxt is this. So here kxt is same as ktx. Here we are considering a real, so bar is not playing any role. So kxt is equal to ktx for this particular example. If you remember, this is of one more type, that is separable type. So you can solve with the help of separable type also, but we are solving this with the help of theory which we have developed earlier. So here we need to find out, say, eigenvalues and eigenfunction. Then to find out eigenvalues and eigenfunction, let us consider the homogeneous version. Homogeneous version means this f of x is not there, so we are considering this homogeneous problem, that is y of x equal to lambda minus 1 to 1 xt plus x square t square yt dt, and we want to find out the values of lambda for which we have a non-trivial solution, and those values we are saying that it is eigenvalues and corresponding solution eigenfunction. So we are solving this with the help of method which we have developed for separable kernel. So we are writing this as lambda x minus 1 to 1 t y t dt plus lambda x square minus 1 to 1 t square y t dt. Now this quantity is something which is a constant, call it c1, and this quantity minus 1 to 1 t square by t is another constant which we call as c2. So yx is written as lambda c1x plus lambda c2x square. So solution we already know, only thing is we need to find out this c1 and c2. So for that we use the expression for c1 and c2 and use the value of y of x. So here we have c1 is equal to this and c2 equal. So using yt given by 21, you can get two equation 23 and 24, c1 1 minus 2 lambda by 3 plus 0 times c2 equal to 0, and this thing. Now if you remember, by solving this is nothing but algebraic equation, d lambda c1 this d lambda of c1 and c2 equal to this thing. So here your d lambda is the coefficient matrix of this algebraic equation. So d lambda is coming out to be modulus of 1 minus 2 lambda by 3 0 0 1 minus 2 lambda by 5, and if you look at this is simply a triangular matrix, and here you can get your eigenvalues very easily, and you can say that lambda 1 equal to 3 by 2 and lambda 2 is equal to 5 by 2 is the eigenvalues, means for which your d lambda is having 0 determinant. So here eigenvalues we know, then we need to find out the corresponding normalized orthonormalized eigenfunction. So for that let us start with the first, that is lambda equal to lambda 1, that is 3 by 2, and you try to solve this 23 and 24. So when you put lambda 1 equal to 3 by 2 here in 23 and 24, then you look at that the first equation 23 is simply redundant because this quantity is 0, so 0 times c1 plus 0 times c2 equal to 0. So this is simply will not give anything. So if you look at here, by putting this you can get that c2 equal to 0 and c1 is completely arbitrary. So when we have c1 is completely arbitrary, then you can write down our solution y1x here we can put the value of C2. So C2 is 0 here, so Yx is lambda C1x. So I can say that lambda is basically what? Lambda is 3 by 2 here. So I can write Y1x is equal to 3 by 2 C1x. So corresponding to this eigenvalue lambda 1 equal to 3 by 2, we have a non-trivial solution, that is 3 by 2 C1x. Now with the C1 is some arbitrary constant, so we can always take C1 in a way such that this 3 by 2 C1 is 1. So we can say that your y1x equal to x is the eigenfunction corresponding to lambda 1 equal to 3 by 2. Similarly, we can find out eigenfunction corresponding to 5 by 2, but we need normalized eigenfunction. So first let us normalize this y1x. So normalize means you just divide by norm of this. So what is the norm here? So norm here is minus 1 to 1 y1x square d of x. Now if you calculate y1x is x here, if you calculate this quantity is coming out to be this 2 by root 6. So so you just calculate and divide by this. So psi 1x is given by this root 6 by 2 x. So this is very easy to solve. Okay. So now lambda 1 is known to you, psi 1 is known to you. Now repeat the same procedure for lambda 2. So lambda 2 is 5 by 2. So first equation gives you this, and second is again the same way redundant. So here you can solve and you can say that C1 is coming out to be 0 and C2 is arbitrary. Again using the solution, this 21, C1 is simply 0, so Yx is nothing but lambda C2 x square. So here lambda is 5 by 2, so it is y2x is 5 by 2 C2 x square. Now again in the same way C2 is completely arbitrary, so we can always consider C2 as 1, and so y2x is your x square is the eigenfunction corresponding to eigenvalue 5 by 2. Now you normalize it, so when you normalize it you divide by norm of this. So norm is minus 1 to 1 y2 square dx. So y2x is x square, simply put it here, and then you can find out that psi 2x is under root 10 by 2 x square. So once we have psi 1 and psi 2, then you can use our formula which says that our solution, I am just going back to this, and here we say that the solution is written as yx equal to f of x plus lambda m equal to 1 to infinity fm upon lambda minus lambda psi mx. Here m is from 1 to infinity, but here in our particular example we have only 2 eigenvalues. So this infinite sum is reduced to only finite sum, that is m equal to 1 and 2. So what we want, we already have lambda 1 and lambda 2, and psi 1 and psi 2 we have. Only thing we have to calculate is f1 and f2. So to calculate f1 and f2 are Fourier coefficient corresponding to f. So f1 is basically what? Minus 1 to 1 f of x psi 1x dx. So psi 1x is already known to you, you put it here, and fx is already known to you, so you can get the value of f1, that is 2 root 6 by 3. This quite simple calculation, you just plug in and then you can find out f1. Similarly in the same way you can find out f of 2. F of 2 is minus 1 to 1 f of x psi 2x. So this is the Fourier coefficient corresponding to this psi 2. So again you can put it all values, already you know f, you know psi 2, you can get your f2. F2 is coming out to be 8 root 2 by 15. So now you know lambda 1, lambda 2, psi 1 and psi 2, and f1 and f2. You just write down your solution as yx equal to fx plus lambda m equal to 1 to 2 fm upon lambda m minus lambda psi mx. So here lambda is 1, we have taken as 1, so fx is this, f1 is this f1 psi 1x upon lambda 1 minus 1 plus f2 psi 2x upon lambda 2 minus 1. So putting all the values, we have yx is equal to 25 by 9 x square plus 6x plus 1. So let us consider one more example to have a better understanding. I hope this is not very difficult. Let us look at this problem, yx equal to 1 plus lambda 0 to pi cos of x plus t yt dt. Now here again you look at cos of x plus t is a symmetric kernel. So it means that if you interchange, it is first of all real, then if you interchange the role of x and t, then cos of x plus t is same as cos of t plus x. So it is a case of symmetric kernel, and then we try to find out. So here f of x is simply 1, and since lambda is not given any constant value, so we can say that lambda is same as lambda. So to find out the solution in terms of resolvent kernel or using our theory, we need to calculate our eigenvalues and eigenfunction. So consider the homogeneous equation, that is you take simply fx as 0. So consider this y of x is equal to lambda 0 to pi cos of x plus t yt dt. Now we want to find out, say, eigenvalues and eigenvectors. So this is you can solve using the method of separable kernel. So you can find out eigenvalues and eigenfunction with the help of method we have discussed for separable kernel. So here you write down cos of x plus t as cos x cos t minus sin x sin t yt dt. Now again you simplify, then it is 0 to pi cos t yt dt minus lambda sin x 0 to pi sin t y t dt. Now this quantity is again constant, call it C1. This is this quantity is your constant, call it C2. So it means that your yx is already known to you. So this is lambda cos x C1 minus lambda sin x C2. So only you need to find out this C1 and C2. So so here using this we already know that C1 is 0 to pi cos t yt dt and C2 is 0 to pi sin t yt dt. So C1 and C2, and you already know the solution y like this. So from this you can calculate yt, put it back to C1 and C2, you can have these two equations, C1 2 minus lambda pi plus 0 times C2 equal to 0, and this 32, equation number 32. And this is again if you look at, this is again a triangular equation to solve, and here your eigenvalue can be find out by, say, coefficient matrix, determinant of coefficient matrix, and determinant of coefficient matrix is nothing but d lambda. And when you solve this you will get that we have two eigenvalues, that is lambda 1 is equal to 2 by pi and lambda 2 equal to minus 2 by pi. So eigenvalues is with us. Now we try to find out the corresponding eigenfunction. So let us start with lambda equal to lambda 1, that is 2 by pi. So when you put lambda equal to lambda 1, that is 2 by pi, then first equation is simply redundant, and you can solve this, and you can say that C2 is coming out to be 0 and C1 is arbitrary, as we have considered in the previous case. So here we say that C2 is 0 and C1 is arbitrary, and we says that look at equation number 29. So yx is already given. So using C2 equal to 0 and C1 arbitrary, y1x is equal to 2 by pi C1 cos of x. Again in a same way which we have already discussed, you can take 2 by pi C1 as 1, C1 is arbitrary. So y1x is your cos of x is the corresponding eigenfunction. So just normalize it. So how to normalize it? You divide it by norm. Norm here is a to b. A is what? 0 and b is pi. So I think it is already cleared here. A is 0 and b is pi. So 0 to pi y1x square d of x half. So this is the norm of y1. So divide by this, and it is this quantity is simply pi by 2. So this is what? 2 by pi root of 2 by pi cos of x. So similar, so this is the eigenvalue, normalized eigen function corresponding to lambda equal to pi by 2. Now let us do the same procedure for lambda 2 equal to minus 2 by pi, and you can say that in the same way you can get C1 equal to 0 and C2 is arbitrary, and you can write down the corresponding non-trivial solution as y2x, and it is minus of minus 2 by pi C2 sin x. Again you can take this constant as 1, and y2x is nothing but sin of x is the corresponding eigenfunction. You can again normalize in the same way. So psi2x is y2x divided by norm of y2x, which is nothing but this quantity. So please I hope we already know norm of y of x is equal to a to b y of x square d of x 1 by 2. Okay. By the way, this is a dummy variable, so you can use t or anything. I am using t because I am using x here. Okay. So this is norm of y of x. So that's why we are dividing by norm of this. So here we have psi2x is given to you. Now in a the similar way we can find out f1 and f2, which is a Fourier coefficient of f corresponding to these eigenfunction psi 1 and psi 2. So f1 is 0 to pi a to b, so a to b means 0 to pi fx psi 1x dx, and you can say that it is coming out to be 0, and f2 is 0 to pi f of x psi 2x dx, which you can calculate, it is coming out to be this quantity 2 upon 2 by pi square root of this, 2 into square root of 2 by pi. So f1 f2 is known to us. Now you simply put it back to your solution, and now problem is that this lambda is not given any constant value. So your solution will also depend on the value of lambda, because lambda we can take any constant. So right now we have a choice that lambda is none of the eigenvalues, one of the eigenvalues, you can take this thing. So let us consider the case when lambda is say taking no values taken as lambda 1, lambda 2. So lambda is neither lambda 1 or lambda 2. So in this case you have yx equal to f of x plus lambda m equal to 1 to 2 fm psi lambda m minus lambda psi mx. So writing f1 and f2, you can get this solution like this. Now if you look at here, look at this 2 plus lambda pi. So if so in case when lambda is neither of these eigenvalues, you can write y of x as this. Now in a second case when lambda is equal to lambda 2, so if you look at lambda equal to lambda 2 here, then this is something which creates problem. Now here lambda is lambda 2 means denominator is 0, and if you look at numerator, lambda is some fixed quantity. Now look at this, psi 2 is non-zero, so only thing depend on this f2 now. Now if f2 is again 0, if f2 is coming out to be 0, then it is kind of 0 by 0 form, right? And in this case this can take any value. So right now we say that f2 is non-zero, which we have calculated by equation number 34, that f2 is non-zero. So in this case it is a 0 non-zero divided by 0, so this cannot happen. So it means that in this case when lambda is equal to lambda 2, that is minus 2 by pi, we do not have any solution. So it means that no solution exists if lambda has value minus 2 by pi. Now let us take lambda equal to lambda 1, that is 2 by pi. Now in this case f1 is coming out to be 0, that is calculated here 33. So it means that here your f1 is 0, denominator is also 0, so it is kind of 0 by 0 form. So this I can take any value a. So if this limit exists, we call it any value. 0 by 0 is you can take any value, a can take any value. So here we have infinite many solution. So I can write it a psi 1x plus lambda upon lambda m minus lambda fm psi mx. So here lambda m is your 2, okay. So here I can write a is any arbitrary constant, and this lambda m is lambda 2. So you can put it the value here, and you can say that it is 1 plus c cos x minus 2 by pi sin of x, where c is this, and since a is arbitrary, c is also an arbitrary thing. So in this particular case if lambda is one of the eigenvalue and if the corresponding Fourier coefficient is non-zero, then we have no solution, as we have discussed in case 2. But if lambda is one of the eigenvalue and the corresponding Fourier coefficient f1 say fi whatever is 0, so it means that when lambda takes eigenvalues and the f non-homogeneous term is orthogonal to the corresponding eigenfunctions, in that case we have infinitely many solution, and in this we can see in a this we have already discussed in the case when we have separable kernel. So in case of separable kernel, this case we have already discussed for the example when we have taken the kernel kxt as 1 minus 3xt. So here we are considering the same case, that lambda equal to lambda 1. So lambda is taking the first eigenvalue, and f1 is 0 means that f is orthogonal to the first eigenfunction corresponding to the eigenvalue here. So if it is the case, then we have infinite many solution, and if that lambda is lambda 2, and f is not orthogonal to the second eigenfunction, then we do not have any solution. So we have these many cases. Now with the help of this, now let us consider this Fredholm integral equation of the first kind. Here again we use Hilbert-Schmidt theorem, which says that if we have fx equal to kxt gt dt, then where k and g both are L2 functions, then fx can be written as your linear combination of eigenfunctions corresponding to kxt. So that we already, so Hilbert-Schmidt theorem we are assuming. So here let me write it here. So here we are using, this is the Hilbert-Schmidt theorem, that f of x is equal to a to b k of xt gt dt, and if k and g both are L2 function, then f can be written as summation of ai phi I x and summation over I, and where phi x is the normalized eigenfunction corresponding to this kernel k. So it means that we are solving this y of x is equal to lambda I to b k of xt and phi yx. So here phi ix is the solution of this. So let me write it here, phi x lambda I phi it. Okay, and this Fourier coefficient here fi is related to Fourier coefficient gi like this. So here you can say that your fk is written as gk divided by lambda k. This we discussed earlier. So here I can write gk as lambda k fk. Now if you look at unknown function, we are assuming in the first kind we are assuming that this g is the unknown function which we are discussing. So how to construct this unknown function from the Fourier coefficient of this unknown function g. So here we have to recall the Ries-Fischer theorem, which says that if we have say this gk, right. So if this series is absolutely and uniformly convergent, then we have a function g of course in L2 such that this g has this representation, gx is minus the summation this ak, sorry, this has this representation gk and phi k x, k is equal to 1 to n is tending to 0. Okay, or you can say that that g has this representation. Okay, so so you can write that if this infinite series, if this infinite series, if it diverges, then we do not have any solution, but if it converges, then Ries-Fischer theorem says that your solution gx can be written as this limit of this infinite series. Okay, and this limit this Ries-Fischer theorem says so. So it means that everything depend on this infinite series. So let us take one simple example here. So let us take this example here, f of x equal to 0 to 1 kxt gt dt, where kxt is given by this. So here it is the Fredholm integral equation of the first kind. Then we need to find out that this is falling in this category. I need to find out fk and gk, all these things. So eigenvalues we need to find out, and eigenfunction we need to find out. So for that corresponding to this we need to find out the eigen value and eigen problem. So here for that we need to find out, we need to solve this, where kxt is given by this this thing. So to find out this we can, let me write it here. So this is what, so here I can write it, phi of x equal to lambda here it is 0 to 1 kxt and your phi t dt. Okay. So from this you can easily say that by conversion of this integral equation into corresponding boundary value problem, you can say that the corresponding boundary value problem is this: d2y by dx square plus lambda y equal to 0, with the boundary condition that y of 0 equal to y of 1 equal to 0. So that is clear from this equation, that y of 0, when you put it here, so y of 0 equal to y1 equal to 0. So to solve this, we have to solve this particular problem. So I think this is quite a simple problem, and you can say that in this case your lambda i's are simply what, pi square, and basically it is n pi square, n pi whole square, and the corresponding eigen functions are root 2 sin pi x, root 2 sin 2 pi x, and you can say that root 2 sin n pi x are your eigen functions. So it means that corresponding to this kernel, look at the eigenvalue problem, that is g of x equal lambda 0 to 1 kxt gt dt, and you look at that this is equivalent to the boundary value problem here. So find out the solution here. So whatever be the solution here, we have the solution here, and the values for which we are getting a non-trivial solution here, the same will be non-trivial solution here. So it means that solving this problem is equivalent to solving this problem. So here we are finding the lambda for which we have a non-trivial solution. So lambda is coming out to be n pi whole square, and the corresponding eigen functions are this. So now you can calculate your Fourier coefficient fk like this: root 2 0 to 1 sin k pi t ft dt. Now with once we have fk, you can calculate fk and lambda k square. Now this is this quantity pi to power 4 k equal to 1 to infinity k 4 fk square. Now if this series converges, then you can write down your g as this limit. So once this lambda fk, this series is convergent, then you can write your gx as limit of this series. So it means that we need to find out fk such that this series is convergent. Once this series convergence, you can find out your solution g. Is that okay? So we will discuss some more problem in our exercise. So thank you for listening us. We will meet in next lecture. Thank you.